nuclear. It's pronounced nuclear. Okay, so we're talking about nuclear reactions here, and we're going to talk about both fission and fusion. So let's start in the world of fission. We've already seen that when we have nuclear fission, we are going from heavier elements into lighter elements. So we're going from high on the periodic table, things like uranium, to things lower on the periodic table, to things like lead. In doing so, we're going to get energy out of our fission until we reach iron. Iron is that iron peak. Whenever you go fizzing or fusing towards it, once you hit it, you're done. You need some extra energy to do that. But in terms of fission, what we're doing is we're taking heavy things and breaking them apart into smaller things. Now, our first fusions, or our first fissions, really took place in the 1930s. Enrico Fermi, who really is like the pioneer of some of this stuff, had an idea. And his idea and his question that he asked was this: if you want something to strike the nucleus of an atom, what would be the best choice? Well, choosing an electron would be negative and the nucleus is positive, so maybe they'd be attracted. But we run into an issue of the outer shells of an atom are negatively charged, so you get a repulsion effect. And a proton is positively charged, which so is the nucleus, so they might want to repel, so that's not a great choice. The best choice to strike a nucleus is a neutron. It's a fairly large particle, so you get a nice cross-sectional area to kind of blast something. Blast him! And it's neutral, so it should just be able to move through. And as long as it hit and it stayed on target, it should hit the nucleus and something should happen. So, Enrico Fermi does this. They set up a fission reactor, and some of the first ones were actually set up at the University of Chicago. And I think they set them up either under the tennis courts or a football field. Just in case anything went wrong, it was just in a kind of open space that they can kind of say, oh, this is done forever. Luckily, that didn't happen. If we take this neutron, though, and we try to strike something, let's write out how that would look as an example. So let's take a neutron, N01, and let's fire it at something. Let's fire it at, let's pick uranium. Uranium is the 92nd element, and we're going to choose uranium 235. There are many different isotopes of uranium. We're just picking 235 here. Now, when this neutron strikes the uranium, something is going to happen here. Well, it's going to stick. We get uranium 92, but it's going to be uranium 236. It's still uranium. Same number of protons. Same atomic number, 92. But we've added another neutron. However, when we added this extra neutron, we made this uranium atom extremely unstable. So unstable that in a time period of about 10 to the minus 12th seconds, it's going to decay. It's going to turn into something else. One such product it could turn into is the following. Barium-141, Krypton-92, and what often happens is we get 3 neutrons kicked out as well. Note that if you added up 141, 92, and 3, because there's 3 neutrons, you'd get back 236, which is what you'd also have in the beginning. Notice we've just conserved atomic mass number and atomic number here. This is a fission reaction, but this is a possible fission reaction, which we'll talk about in a second. In general, we can write a fission reaction, or a common fission reaction, as follows. It's going to be the neutron. It's going to be uranium-235. It's going to kick to uranium-236. But then over here, we could have two different elements. 1 and 2. And then we get some neutrons. This is a generalized case of what could happen. I say generalized because until that fission product actually occurs, until we actually take uranium-236 and it fissions in that brief period of time, we don't know what we're going to get. In fact, we only know a probability of what we're going to get. With atomic number and statistical percentage here, we actually get a graph that kind of looks like this. It's a bimodal bump. These two peaks right here, these correspond to the two elements we saw before. But that doesn't mean they always need to be created. We could have two different elements created instead. This goes down to about a Z value of 72. That's a bad looking 2. Give or take. It's not a perfect graph there. But there is a probability that you could have a fission of uranium and get identical products. It is possible. Is it likely compared to getting barium and krypton here? No. It's very unlikely. But it is possible, and we do see it. The wild thing about this is that in these kind of setups here for fission, we kick out 3 neutrons. We'll see later on why this could be a potentially dangerous and catastrophic occurrence when we kick out these extra neutrons. But this is a generic fission product. We are taking a massive quantity, some massive, large nucleus, and we are splitting it. And when these split, they actually kind of, they make a pseudo figure 8 pattern. It looks kind of like mitosis when it happens. But as a result, maybe this figure 8 is larger on one end than the other, and we get our fission. Okay? So this is a standard fission that we see here. It's nothing too crazy in the realm of nuclear decays, and it's what we do use to power our reactors. In terms of fusion, there are many different pathways through fusion, and it starts to really get into some complex things with hydrogen. But in general, fusion typically begins with 2 hydrogens. What they make out of this can actually vary a little bit. In some instances, you can get like a helium-2 out of it, like helium-2s. But really, where we tend to see nuclear fusion in this regard is really in the heart of stars. Really, stars are the only spots that we've been able to, well, not even we, but just the universe has been able to successfully maintain and continue long-stage nuclear fusion. And in doing so, it actually goes through a number of different stages. You actually end up getting heliums and hydrogens back out of this, and then those heliums and hydrogens that you get out of this kind of combine into things, and then those kind of take off, and then you get a little bit of hydrogen back in the end, and then you get a little bit of helium. So you don't like burn all your hydrogen, you keep a little bit of it, and you get some helium out of it. It gets kind of weird. There's all sorts of different cycles that occur with this. There's like the, it's called like the proton-proton chain, which is the beginning of this here. And there's all sorts of like different things here. I think there's like a CNO cycle as well. It's like a carbon, nitrogen, oxygen cycle that you like build up through those. But stellar nucleosynthesis gets kind of weird, so we're not going to cover it in depth here. The main takeaway from it is you start with hydrogen and you work your way up there until you get to iron. There are many different chains that take place in this, but really here on Earth, we haven't been able to harness this power yet, and for a long period of time now, we've been trying to do so. One of the best and most recent advancements we have is something known as the Tomahawk Reactor. We are trying to use large magnetic fields combined with high pressures and temperatures to start a fusion reaction, and we are trying to see if we can keep a fusion reaction going. If we could, we'd kind of be like Spider-Man 2 with Doc Ock whenever Tobey Maguire was the Spider-Man. And in that case, you know, we have harnessed the power of a star. Because if you can keep fusion just going, you don't get the harmful radioactive products that we do off of a fission cycle, and you get actually a lot more energy out of it than you do with fission cycles as well. So if we are able to harness the power of fusion, that'd be very, very powerful for mankind. But we're just not there yet. Okay, so with that, we're mainly going to stick with fission here. We have this equation. We're going to cut this short now, but in our next video, we'll start talking about some of the problems we have with trying to build things like reactors, which use fission, and how we can overcome some of those difficulties. But until then, this is finished. Until next time, adios. Take it easy.